Everything you see around you, your body, the stars, even the air you breathe, is made of things so small that billions of them would fit on the tip of a needle. We call these tiny things particles, and we thought they were like solid little balls floating in space. But when scientists looked closer, they discovered something that changed everything. Particles are nothing like we imagined. They can be in two places at the same time, pass through solid walls, and even communicate instantly across the entire universe. And the most shocking part, they only decide where to be when someone looks at them. How can something so small break all the rules of reality we know? Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. What are the smallest things that make up everything around us? Particles are the smallest parts that make up all matter. They are very small. They cannot be seen with the eye. Everything we touch and all things we see are made from many particles. Particles are inside solids. They are inside liquids. They are inside gases. Parts of our bodies are made of particles. The air we breathe is made of particles. The water we drink is made of particles. Some particles join to make atoms. Atoms are units with a center and parts around that center. Atoms join to make molecules. Molecules form the materials in our world. Other particles do not join to form atoms. Those particles move on their own. They carry energy. They carry forces between pieces of matter. Particles have properties. These properties help to decide how particles act. One property is mass. Mass is a measure of how much matter a particle has. Mass can be large or small. Some particles have no mass. Another property is electric charge. Electric charge can be positive, negative, or zero. Charge makes particles feel the electric force. Particles with the same sign of charge can push each other. Particles with opposite signs can pull each other. Spin is another property. Spin is a basic part of a particle's identity. Spin can take certain values. Spin affects how particles can be arranged and how they behave with other particles. Some particles are stable. Stable particles can last for a very long time. Some particles are unstable. Unstable particles change into other particles. This process is called decay. When a particle decays, new particles appear. In these changes, some things do not change. For example, electric charge does not disappear in particle changes. Total energy also does not disappear. These ideas are rules that scientists use to predict which changes can happen. There are many kinds of particles. Scientists give names to the main kinds. Three very common names are electron, proton, and neutron. Electrons are particles with negative electric charge. Electrons are found around the center of an atom. Protons have positive electric charge. Protons are in the center of an atom. Neutrons have no electric charge. Neutrons are also in the center of an atom. Electrons, protons, and neutrons are the parts that build ordinary atoms. Protons and neutrons are not the smallest parts. They are made of smaller parts called quarks. Quarks are more basic than protons or neutrons. There are different kinds of quarks. Quarks carry electric charge. Quarks join inside protons and neutrons. The force that holds quarks together is very strong. This force works only at very small distances inside protons and neutrons. Some particles carry forces. Photons are particles of light. Photons carry the electromagnetic force. The electromagnetic force acts between charged particles. Photons can move through empty space. They carry energy from one place to another. Gluons carry the strong force that keeps quarks together. W and Z bosons carry the weak force. The weak force plays a role in particle decay. The Higgs boson is a particle that is linked to how some particles get mass. Neutrinos are very light particles. Neutrinos pass through most matter almost without change. They are hard to detect because they interact very weakly with other particles. Scientists group particles into two broad sets. One group is called fermions. Fermions make up matter. Electrons, protons, neutrons, and quarks are fermions. Fermions follow a rule that keeps many of them from being in the same state at the same time. This rule helps explain why matter can have structure and volume. The other group is called bosons. Bosons carry forces. Photons, gluons, W and Z bosons, and the Higgs boson are bosons. Bosons can share states with other bosons. This allows them to act in ways that are different from fermions. Particles can be heavy or light. Some particles have a lot of mass. Some particles have very little mass. Some particles have zero mass. Mass affects how particles move and how they feel forces. The electric charge of a particle affects how it responds to the electromagnetic force. Spin and other properties affect how particles combine and how they behave under force. Particles can have a size that we can describe with words. In many cases, particles are point-like in our experiments. That means they have no size that we can measure with current tools. At other scales, we can think of a particle as a region where certain effects happen. For atoms, we can describe the space where electrons are likely to be found. That space is much larger than the center of the atom. The mass of an atom is mostly in the center of the atom. The space that defines the size of an atom is mostly where the electrons move. Particles are not always easy to see because they are so small. To study particles, scientists use careful experiments. They use special machines and detectors. They speed up particles and let them collide. They record the signals from those collisions. They use math to analyze the results. They repeat tests many times. They check results carefully. This work helps them find the names and properties of particles. It helps them learn the rules that particles follow. Some particles are easy to detect. Electrons and protons are easy to find in many experiments. Photons are easy to detect by light detectors. Other particles are hard to detect. Neutrinos are hard to detect because they pass through matter with little change. Some particles exist only for a very short time. These particles appear in high-energy collisions. They last for a short period and then change into other particles. To study them, experiments need high-speed detectors and careful timing. The behavior of particles can be surprising. Particles do not always act like tiny solid balls. At very small scales, particles show behaviors that need new rules to describe them. These rules are part of a theory called quantum mechanics. Quantum mechanics uses math to give probabilities for different outcomes. It tells us how likely it is to find a particle in a certain place or with certain properties. The math works well in many experiments. It gives numbers that match what detectors record. Particles can move, and they can also carry energy. Photons, for example, are particles that carry energy in the form of light. When photons meet matter, they can give or take energy. This exchange of energy is the basis of many effects in light and materials. Electrons carry electric charge and also carry energy when they move in a material. The control of electron flow is the basis of many devices in electronics. Forces between particles are important. The electromagnetic force acts between charged particles. It holds electrons near atomic centers. It also holds atoms together to make molecules. The strong force acts at very small distances. It holds quarks together inside protons and neutrons. It also helps hold protons and neutrons together inside the center of an atom. The weak force changes particles in certain reactions. It plays a role in how some particles decay. Gravity also acts on particles. Gravity acts between masses. Its effect on small particles is very tiny in many experiments, but it is important at very large scales. Names help us talk about particles. The word electron tells us we mean a particle with negative electric charge that often moves outside the center of atoms. The word proton tells us we mean a particle with positive electric charge that is in the center of atoms. The word neutron tells us we mean a particle with no electric charge that is also in the center of atoms. The word photon tells us we mean a particle of light. The word neutrino tells us we mean a very light particle that passes through matter. The word quark tells us we mean a part that joins to form protons and neutrons. The word Higgs boson tells us we mean a particle linked to mass. These names are short labels for ideas. Scientists use these names to tell others what they measure and what they expect in tests. Scientists build models and use math to describe particles. A model is a set of ideas that gives predictions. The current main model for known particles and their forces is called the Standard Model. The Standard Model lists the known particles and gives rules for how they interact. It groups particles into families and shows which particles carry which forces. The Standard Model has been very successful in predicting the results of many experiments. At the same time, it does not explain everything. There are phenomena that are not yet part of the Standard Model. Scientists search for new particles and new rules to explain those phenomena. Particles can be created and destroyed in certain processes. Energy can change into matter, and matter can change into energy. When this happens, some quantities remain the same. Electric charge remains the same overall. Total energy remains the same overall. These conservation rules guide which reactions can occur. In high-energy collisions, scientists can create new particles. They then watch how those particles change and what signals appear in detectors. This is one way to discover new particles. The study of particles has led to useful tools. Electronics depend on the quantum behavior of electrons. Transistors control electron flow in circuits. Semiconductors are materials that guide electrons in controlled ways. Lasers and light-emitting diodes depend on particle behavior in atoms and materials. Medical tools, such as certain imaging devices, rely on particle properties. Precise clocks use atomic properties to keep time. Microscopes that use electrons let scientists see structures that are too small for light microscopes. These tools show that learning about particles can lead to new technologies. People who study particles come from many fields. They include experimental scientists who run machines and collect data. They include theoretical scientists who make models and write math to explain the data. They include engineers who build detectors and machines. They include computer experts who manage the large sets of data that come from experiments. This work needs careful design, testing, and review. Teams work together to check results and to repeat tests. This process makes the findings stronger. Language and simple ideas help to teach what particles are. It is useful to learn the main names and the basic properties. It helps to know that some particles make up matter and other particles carry forces. It helps to know that particles can be stable or unstable. It helps to know that particles can be created or destroyed under certain rules. It helps to know that scientists use machines and math to study particles. These facts form the basic picture of the particle world. A few more simple facts can help the listener. Atoms are usually electrically neutral overall. That means the total negative charge of the electrons is balanced by the total positive charge of the protons inside the atom. If an atom gains or loses electrons, it becomes charged. A charged atom is called an ion. Ions have a net electric charge. Ions play a role in many chemical and physical processes. particles can carry the same set of properties in many copies. For example, many atoms of the same element have the same number of protons. That number sets the type of element. The number of protons in the center of an atom is a key property for how that atom interacts with other atoms. The arrangement of electrons around the center determines many chemical properties. When atoms join into molecules, electrons often move between centers or are shared. These electron arrangements explain why materials have different properties. The world of particles is broad. It includes very light particles and heavier ones. It includes stable particles that last a long time. It includes unstable particles that change quickly. It includes particles that make up atoms and particles that carry forces between atoms. The study of particles helps us to understand the structure and behavior of matter at the smallest scales that we can measure. Knowing the names of the main particles gives a foundation. Electrons, protons, neutrons, quarks, photons, neutrinos, and the Higgs boson are central names to remember. Knowing the basic properties gives a second part of the foundation. Mass, electric charge, and spin are three important properties. Knowing that particles can be stable or unstable and that they can be created or destroyed under rules gives a third part. Atoms are built from these particles. The center of an atom holds protons and neutrons. Electrons are found around that center. The parts of atoms and how they join to make molecules shape the materials we see. Understanding the parts of atoms and how they hold together is the natural next step in learning how particles build the world. Atoms are the small structures that particles build. Their parts explain how matter holds together and how it acts. An atom has a center. That center is the nucleus. The nucleus contains protons and neutrons. Electrons move around the nucleus. These parts give an atom its most important properties. A proton carries a positive electric charge. A neutron carries no electric charge. An electron carries a negative electric charge. The number of protons in the nucleus is a key trait of an atom. That number defines the element. For example, an atom with 1 proton is hydrogen. An atom with 6 protons is carbon. Scientists use the number of protons as the basic label for each element. Protons and neutrons together set the mass of the nucleus. The mass of an atom comes mainly from its protons and neutrons. Electrons have much less mass than protons or neutrons. Still, electrons determine the space that the atom occupies. Electrons move in regions around the nucleus. That region is often called the electron cloud or electron shell. The size of an atom is set by where its electrons are most likely to be found. Protons and neutrons are not the smallest parts of matter. Each proton and each neutron is itself made from smaller parts called quarks. Quarks carry electric charge in fractions. For the common quarks inside protons and neutrons, one type has a charge of 2/3 and another type has a charge of -1/3. A proton is made of 2 quarks of the 2/3 type and 1 quark of the -1/3 type. The sum of those charges gives the proton a net +1 electric charge. A neutron is made of 1 quark of the 2/3 type and 2 quarks of the -1/3 type. The sum of those charges gives the neutron no net charge. A force called the strong force holds quarks together inside protons and neutrons. The strong force also helps hold protons and neutrons together inside the nucleus. The particles that carry the strong force are called gluons. Gluons move between quarks. They act to bind quarks into protons and neutrons. Inside the nucleus, the strong force works at very short distances. It keeps the nucleus bound even though protons have positive electric charge and push away from each other. The balance of forces inside the nucleus is a central idea in how atoms stay intact. Electrons feel the electric force from protons. The electric force pulls electrons toward the positive protons in the nucleus. At the same time, electrons have motion and energy that keep them from falling into the nucleus. The combination of these effects leads to allowed states for electrons. These states have specific energies. Electrons in an atom can occupy only certain allowed energies. When an electron changes from one allowed energy to another, it can absorb or emit a particle of light. That particle of light is called a photon. Photons carry energy away or bring energy into the atom. The energies of the photons correspond to the differences between the allowed electron energies. These energy changes explain why atoms can absorb or emit light at well-defined colors or frequencies. The arrangement of electrons around the nucleus determines how an atom behaves chemically. Electrons in the outer region of the electron shell are the ones that often take part in chemical change. These outer electrons are commonly called valence electrons. Atoms with the same number of valence electrons tend to show similar chemical behavior. That regular pattern is the basis for the organization of the periodic table. The periodic table lists elements in an order that reflects their electron arrangements. As a result, the chemical properties of elements show regular patterns across the table. Atoms can join together to form molecules. When atoms join, their electrons change the way they are shared or held. Two common ways to form a bond between atoms are by transferring electrons and by sharing electrons. When one atom gives an electron to another, each atom may end up with a net electric charge. A charged atom is called an ion. Ions of opposite charge attract each other by the electric force. An arrangement of ions that holds together is an ionic bond. When two atoms share one or more pairs of electrons, the shared electrons belong to both atoms in the molecule. This shared arrangement is called a covalent bond. Covalent bonds let atoms form stable groups that act as single units. Many molecules form by covalent bonds. Some materials form when many atoms share electrons in a way that lets electrons move across many atoms. In these materials, electrons are not held tightly by any single atom. The motion of electrons over many atoms gives these materials properties that are useful in many devices. The controlled motion of electrons is the basis of electronics. The way electrons move in materials depends on how atoms and their electrons are arranged. Atoms can gain or lose electrons. When an atom gains an electron, it becomes a negatively charged ion. When an atom loses an electron, it becomes a positively charged ion. Ion formation happens in many chemical reactions and in processes such as the passage of electric current through a solution. Ion formation also plays a role in biological systems and in the function of batteries. Isotopes are atoms of the same element that have different numbers of neutrons. Isotopes share the same number of protons. They thus have the same chemical identity, but different numbers of neutrons change the atomic mass. Some isotopes are stable and last for very long times. Other isotopes are unstable. An unstable isotope can change into a different atom or into different particles. This change is radioactive decay. There are several kinds of radioactive decay. One kind of decay is the emission of an alpha particle. An alpha particle has 2 protons and 2 neutrons. It is the same composition as a helium nucleus. When an alpha particle leaves a nucleus, the original nucleus loses 2 protons and 2 neutrons. The loss changes the identity of the nucleus. Another kind of decay is beta decay. In one form of beta decay, a neutron changes into a proton and an electron and another particle called a neutrino. The electron that appears in this process can leave the nucleus with some energy. The neutrino also carries away energy and can be hard to detect. In another form of beta decay, a proton can change into a neutron while emitting a positron and a neutrino. A positron is a particle that has the same mass as the electron, but a positive electric charge. A third kind of nuclear process is gamma emission. Gamma emission sends out a photon of very high energy. These gamma photons do not change the number of protons or neutrons in the nucleus. They change only the energy state of the nucleus. Nuclear reactions can release or absorb large amounts of energy. In nuclear fission, a heavy nucleus splits into smaller nuclei and other particles. This process can release energy. In nuclear fusion, light nuclei join to make heavier nuclei. This process can also release energy. The Sun and other stars produce energy through nuclear fusion. In fusion, hydrogen nuclei combine to form helium and release energy that travels as particles and light. These processes show that nuclear changes can convert mass into energy and energy into mass under rules that keep certain totals, such as electric charge and total energy, the same before and after the change. Atoms have discrete energy levels for their electrons. When an electron moves from a higher allowed energy to a lower allowed energy, the atom emits a photon. When an electron moves from a lower allowed energy to a higher allowed energy, the atom must absorb a photon with the right amount of energy. The set of photon energies that an atom can absorb or emit is specific to the atom. These sets are called atomic spectra. Scientists can measure the atomic spectra with instruments that record light at many frequencies. The spectra serve as a fingerprint for the atom. They let scientists identify elements and measure conditions in distant objects, such as stars. The nucleus itself has energy levels. Nuclei can exist in excited states with extra energy. When a nucleus moves from an excited state to a lower energy state, it can emit a gamma photon. Nuclear energy states and transitions have their own rules and their own spectra. Nuclear reactions and nuclear decay are central to fields such as nuclear physics, astrophysics, and medical imaging. The behavior of electrons and the structure of the nucleus are not visible to the eye. To learn about these small parts, scientists use indirect methods. One method is scattering. In scattering experiments, particles such as electrons or light particles are sent at an atom or a nucleus. By measuring where the incoming particles end up and with what energies, scientists infer the structure of the atom and nucleus. Another method is spectroscopy. Spectroscopy records the light that atoms absorb or emit. The pattern of lines gives information about electron energies. Mass spectrometers separate atoms and ions by their mass and charge. They let scientists measure atomic masses and identify isotopes. Electron microscopes use electrons to form images of small structures. These instruments rely on the interaction of electrons with matter to reveal detail at very small scales. Atoms are open systems for many kinds of interactions. They can gain energy from collisions or from light. They can lose energy by emitting light or by colliding with other particles. Chemical reactions rearrange electrons among atoms and can release or absorb energy. Nuclear reactions change the particles inside the nucleus and can release larger amounts of energy. In all of these processes, certain quantities remain the same. Electric charge is conserved. Total energy is conserved. Other conservation rules, such as the conservation of certain particle counts in some processes, also guide what can happen. These conservation rules help scientists predict the outcomes of reactions. The study of atoms links directly to many real-world applications. Knowledge of electron arrangements led to the design of materials that guide electron flow. This knowledge underlies the development of semiconductors and transistors. Understanding atomic spectra allowed the creation of lasers and light-emitting devices. The knowledge of isotopes and nuclear reactions made medical imaging and cancer treatments possible. Techniques that probe atoms also led to tools that can manipulate matter at the atomic scale. These tools depend on precise knowledge of atomic structure and the forces that act inside atoms. Simple labels help to organize the parts of atoms. The word proton names the positively charged particle in the nucleus. The word neutron names the neutral particle in the nucleus. The word electron names the negatively charged particle that moves around the nucleus. The word quark names the parts inside protons and neutrons. The word gluon names the particle that carries the strong force between quarks. The word photon names the particle of light. The word neutrino names a very light particle that can appear in nuclear reactions. These names let scientists describe processes and build theories that match experimental results. Atoms also show that scale matters. The sizes and energies at atomic and nuclear scales follow their own rules. The forces that matter at one scale may be irrelevant at another. For example, the electric force shapes the arrangement of electrons around a nucleus. The strong force shapes the behavior of quarks inside protons and neutrons, and the binding of protons and neutrons in the nucleus. Gravity acts on all mass, but its effect on individual atoms is tiny compared with the electric and strong forces in typical laboratory experiments. Atoms can be parts of larger structures. Collections of atoms form solids, liquids, and gases. In solids, atoms can form ordered or disordered structures. In liquids, atoms or molecules move and slide past one another. In gases, atoms or molecules move freely and fill the available space. The properties of these states depend on how atoms and molecules interact. Temperature and pressure affect the motion of atoms and molecules and can change the state of a material. Chemical reactions change the arrangement of atoms and can form new materials. The language used to count parts in atoms relies on specific words. The number of protons in a nucleus is called the atomic number. The sum of the number of protons and the number of neutrons is called the mass number. Two atoms with the same atomic number but different mass numbers are isotopes. When scientists speak of ions, they name the net electric charge that remains after electrons are gained or lost. These conventions help scientists communicate clearly about the structure and behavior of atoms. Atoms do not always remain unchanged. In many materials, atoms can change partners. Chemical bonds can break and form new bonds. These changes can release or absorb energy. In nuclear reactions, the content of the nucleus can change. These changes can produce different elements or different isotopes. The products of nuclear changes can include particles such as electrons, positrons, neutrinos, alpha particles, and photons. The observation of these products gives clues about the internal processes inside the nucleus. The study of atoms has a long history. Experiments showed that atoms have inner structure. Careful measurement led to the ideas that atoms contain a nucleus and outer electrons. Later experiments revealed that protons and neutrons are not indivisible. Scientists found quarks and the forces that bind them. Each new experimental result added a piece to the picture of atomic structure. Today, scientists continue to probe atoms with sharper tools and to refine the models that describe their parts and their interactions. Understanding atoms gives a firm foundation for the study of the particle world. The identities of protons, neutrons, electrons, and quarks provide the basic vocabulary. The roles of electric and strong forces explain how these parts stay together. The behavior of electrons determines chemical properties and the way atoms form molecules. Nuclear structure and nuclear reactions explain the source of nuclear energy and the production of elements in stars. From this set of facts, scientists build models that explain experiments and predict new phenomena. Knowing the parts of atoms also prepares us to group particles into families. Particles that make up matter share some features. Particles that carry forces share other features. Names and simple rules help to sort particles and to understand why they behave differently. The patterns found in atoms and their parts point toward broader ideas about how the particle world is organized and how the forces act between particles. This organization of particles and forces is a central idea in the ongoing study of matter at the smallest scales. To make sense of the organization of particles and forces, scientists put particles into clear groups. These groups help to name particles and to explain how they act. Group names tell us whether a particle makes up matter or whether it carries a force. The groups also show shared properties and shared rules for behavior. One major division is between matter particles and force-carrying particles. Matter particles form the stuff of atoms and solids and liquids and gases. Force-carrying particles move forces between matter particles. Each group has many members. Each member has simple properties that scientists measure. These properties include mass, electric charge, and spin. They also include how long a particle lives and how it interacts with other particles. Matter particles belong to a family called fermions. Fermions have a property called spin that takes values like 1/2, 3/2, and so on. This spin value leads fermions to follow a rule that prevents many of them from being in the same state at the same time. That rule helps to explain why matter has structure and does not collapse into a single state. Fermions include two main types: quarks and leptons. Quarks are the parts that build protons and neutrons. There are 6 kinds of quarks. Scientists give them short names. They are called up, down, charm, strange, top, and bottom. Each quark carries electric charge in fractions. One kind of quark has a charge of 2/3. Another kind has a charge of -1/3. A proton contains 2 quarks of the 2/3 type and 1 quark of the -1/3 type. A neutron contains 1 quark of the 2/3 type and 2 quarks of the -1/3 type. The quark charges add up to the electric charges of protons and neutrons. Quarks also carry a property that makes the strong force act. Scientists call this property color. Color is not a color we can see. It is a name for the type of charge that the strong force uses. Particles called gluons carry the strong force between quarks. Gluons move between quarks and hold them together inside protons, neutrons, and other hadrons. These bound groups of quarks are called baryons when they hold 3 quarks. Protons and neutrons are baryons. When a quark pairs with an antiquark, the pair can form a meson. Pions and kaons are examples of mesons. Scientists have not seen free quarks. Quarks are always found inside larger particles in experiments. When high energy tries to pull quarks apart, new quarks appear and join to form other particles. This property of quarks is a basic rule of the strong force. Leptons are the other main type of fermion. There are 6 leptons. 3 of them carry electric charge. The charged leptons are the electron, the muon, and the tau. The electron has a negative electric charge and is a stable particle in ordinary matter. The muon and the tau have the same negative charge but have more mass. They live for short times and then change into other particles. The other 3 leptons are neutrinos. Each neutrino is tied to one of the charged leptons. That is, there is an electron neutrino, a muon neutrino, and a tau neutrino. Neutrinos have no electric charge and are very light. They pass through most matter with little change. Neutrinos can change from one kind to another when they move. This change is called oscillation. The fact that neutrinos change kind shows that they have mass, even if very small. The fermions split into 3 generations. Each generation contains 2 quarks and 2 leptons. The first generation is the set used in ordinary matter. It contains the up quark, the down quark, the electron, and the electron neutrino. The second generation contains the charm quark, the strange quark, the muon, and the muon neutrino. The third generation contains the top quark, the bottom quark, the tau, and the tau neutrino. The second and third generations include particles that are heavier and that live for shorter times in typical conditions. In many processes, heavier particles change into lighter particles and produce other particles such as neutrinos and photons. The other broad group of particles are the bosons. Bosons have spin values that are whole numbers, such as 0 or 1. Bosons do not follow the same exclusion rule as fermions. Many bosons can share the same quantum state. Bosons often act as carriers of forces. They move force effects from one particle to another. One familiar boson is the photon. A photon is a particle of light. Photons have no mass. Photons carry the electromagnetic force between charged particles. When charged particles interact, photons are exchanged in the process that transmits the force. Photons also carry energy as light does when it moves through space. Gluons are bosons that carry the strong force. Gluons move between quarks and make the strong force act. Unlike photons, gluons carry the color property themselves. This means that gluons interact with each other as well as with quarks. The interactions of gluons produce the complex behavior of the strong force that binds quarks into protons, neutrons, and other hadrons. The weak force is carried by the W and Z bosons. The W bosons come in 2 electric charge forms, a positive and a negative. The Z boson has no electric charge. The weak force plays a role in changing one type of particle into another. For example, the weak force can change a down quark into an up quark while emitting other particles. The weak force also acts inside certain types of radioactive decay. The Higgs boson is a boson linked to another concept called the Higgs field. The Higgs field fills space and can interact with some particles. These interactions give some particles a property we call mass. The Higgs boson is a quantum of the Higgs field. It appears in experiments when the field is excited and a particle of that excitation is produced. Each force-carrying boson has properties that affect how the force works. Photons have no mass and can travel long distances through space. W and Z bosons have mass. The masses of these bosons affect how the weak force operates at small scales. Gluons have no mass in theory, but the strong force acts at very short distances and binds quarks tightly. The Higgs boson has mass and interacts in a specific way tied to the field that gives mass to some particles. For every particle that exists, there is an antiparticle. An antiparticle has electrical and other charges of opposite sign. The mass of a particle and its antiparticle is the same. When a particle and its antiparticle meet, both can be destroyed and their energy can appear as other particles. For example, an electron meets a positron, which is the electron antiparticle. The electron and positron can disappear and produce photons. Antiparticles apply to quarks and leptons and to many other particles. When a quark meets an antiquark, they can form a meson, or they can annihilate and produce other particles. Some particles are stable. Electrons are stable in ordinary conditions. Protons are very long-lived in the observed universe. Some other particles live for a very short time and change into other particles. The lifetime of a particle is a measured property. It gives the average time the particle will exist before it changes. Lifetime can vary from extremely long to extremely short. Scientists measure lifetimes in many experiments. Particle masses vary from very small to very large. Mass is a measure of how a particle responds to forces and how much energy it contains at rest. Some particles have no mass. Photons and gluons are treated as massless in the theory that describes them. Other particles have much larger mass. The top quark is one of the heaviest known elementary particles. The Higgs boson also has a sizable mass. The masses of particles help determine how they behave and how they can be produced in collisions. Electric charge is another basic property. Charge comes in positive and negative values. The unit of electric charge is the charge of the proton, which is a positive unit. The electron has one negative unit. Quark charges appear in fractional units, such as 2/3 and -1/3. The total electric charge is always conserved in interactions. This conservation law helps to predict which particle reactions can occur. Spin is a fundamental property that affects how particles behave in groups. Fermions have spin values of half units, such as 1/2 or 3/2. Bosons have spin values of whole units, such as 0 or 1. Spin affects the allowed combinations of particles and the patterns of their states. It also affects how particles interact with fields and with each other. Scientists group all known particles and their interactions in a framework called the Standard Model. The Standard Model lists the fermions and bosons and gives rules for how they interact. It explains many experimental results. It tells us how electromagnetic, weak and strong forces act on particles. The Standard Model does not include gravity. That is a separate interaction that affects masses and large-scale objects. The Standard Model has helped to predict the existence of particles that were later found in experiments. It also predicts many interaction rates and particle properties that match measured values. Some particles interact strongly with matter. Charged particles often interact with electromagnetic detectors. They lose energy as they pass through materials and leave signals. Other particles interact weakly. Neutrinos barely interact and pass through most matter. Detecting neutrinos requires special techniques and large detectors. Other particles interact by the strong force and are seen in detectors that record the particles produced when they stop or change. Composite particles are made of 2 or more quarks. Baryons are composite particles made of 3 quarks. Protons and neutrons are baryons. Mesons are composite particles made of a quark and an antiquark. Mesons can be unstable and decay into other particles. Composite particles have properties that come from the quarks and from the forces that hold them together. Particle interactions follow conservation rules. Electric charge is conserved, energy is conserved, momentum is conserved. Other quantities, such as certain particle counts, are conserved in many interactions. Conservation laws limit which reactions can happen. They also guide the interpretation of what detectors record. When scientists analyze collision data, they use conservation laws to reconstruct what particles were present before and after an interaction. The names of particles help scientists to speak clearly. Saying electron identifies the charged lepton with certain mass and charge. Saying up quark identifies the quark with charge of 2/3 that sits in protons and neutrons. Saying photon names the carrier of electromagnetic action that appears when atoms absorb or emit light. These names make it possible to discuss experiments and to write clear rules about interactions. Experiments produce many particles. In high-energy collisions, particles can appear in large numbers for a short time. Detectors record their tracks and energies. From those records, scientists identify which particles appeared and how they transformed. Finding new particles often means linking signals in detectors to the expected patterns that a particle would produce. The Standard Model gives expected patterns for many known particles. When experiments find patterns that do not match the model, scientists study them to see if a new particle or new rule is present. The pattern of particle families and force carriers also points to deeper symmetries. Scientists use mathematical rules to express these symmetries. These rules explain why certain particles appear together and why certain interactions are allowed. Symmetries also predict relations between different processes. When experiments confirm these relations, confidence in the model grows. When experiments disagree, scientists look for extensions or new ideas. New particles can appear in experiments when enough energy is available. Energy can become matter during collisions. The energy needed depends on the mass of the particle that appears. Heavier particles need more energy to be produced. Once created, some heavy particles live for a short time and decay into lighter particles. By measuring the decay products and their energies and angles, scientists can infer the properties of the original heavy particle. Some open questions remain about the particle groups and their properties. For example, the reason why there are 3 generations of fermions is not yet explained by the Standard Model. The pattern of masses across particles is not yet predicted in a simple way by the model. The nature of some particles, such as neutrinos, still raises questions about their exact mass values and whether they are their own antiparticles. Understanding the groups of particles and the roles of bosons and fermions prepares the ground for how particles behave at the smallest scales. The rules that govern particles at those scales are different from daily experience. Those rules use probabilities and wave descriptions to predict outcomes. The groupings of particles, their charges, their masses, and their spins all enter into those quantum rules. The way particles group and interact at the level of atoms and inside nuclei points directly to the need for a quantum description of motion and measurement. Because particles and forces inside atoms follow precise patterns, scientists use a different set of rules to describe their motion and what happens when we measure them. These rules form a subject called quantum mechanics. Quantum mechanics is the name for the ideas and the math that describe particles at very small scales. It gives a clear way to predict chances for different results in experiments. A core idea in this subject is the wave function. The wave function is a mathematical description of a particle or of a small set of particles. The wave function does not give a single definite answer for where a particle is. The wave function gives a set of values that we use to find the chance to get each possible result. To find the chance of seeing a particle in a particular place or with a particular property, scientists use the wave function in a specific calculation. That calculation gives the probability for each outcome. When the wave function tells us a high probability for a place, many measurements will show the particle in that place. When it tells us a low probability for a place, few measurements will show the particle there. If the same experiment is repeated many times under the same conditions, the fraction of times a given result appears tends to match the probabilities from the wave function. This link between the wave function and repeated results is one of the main strengths of quantum mechanics. The wave description does not mean the particle splits into many pieces. The wave function is a description that assigns chances. The particle itself gives a single result when measured. The wave function describes how likely each possible result is. It is a tool to predict and to calculate probabilities. The wave function also changes in time. A rule or equation tells how the wave function moves and evolves. Scientists use that rule to predict how the probabilities change as the system evolves. Using the rule and the wave function, scientists can calculate how the chance of finding a particle in a given place or with a given property changes over time. A quantum state is a term for a full description of a particle given by the wave function and its relevant properties. A state can include information on the energy, on the spin, and on other qualities. When a particle is in a bound situation, such as an electron around a nucleus, only certain states are allowed. These allowed states have specific energies. The set of allowed energies represents the discrete energy levels of the system. Energy levels in atoms are fixed values. An electron in an atom may occupy one of these allowed energies. It cannot have energies in between the allowed values for that bound situation. When an electron moves from a higher allowed energy to a lower allowed energy, the atom emits a particle of light. That particle of light is called a photon. The photon carries away the exact amount of energy equal to the difference between the two allowed energies. When an electron rises from a lower energy to a higher energy, the atom must absorb a photon with exactly the needed amount of energy. The specific energies that an atom can absorb or emit make a pattern of lines in the light that the atom gives off or takes in. These patterns are called spectra. Each species of atom has its own pattern of spectral lines. Scientists use these patterns to identify elements and to measure conditions such as temperature and composition in distant objects. Wave behavior shows itself in other ways too. The wave function can interfere with itself. When parts of the wave function add up, they can make a higher probability in some places. When parts of the wave function subtract, they can make a lower probability in other places. The result of this addition or subtraction is a pattern of high and low chances. These patterns are a direct result of the wave description. Experiments show that single particles can build up such patterns when they are observed many times. In one well-known type of test, particles sent one at a time can produce a final pattern on a screen that matches the pattern predicted by the wave description. Each single detection is a point-like result, but the large number of results together form the wave pattern predicted by the wave function. This effect demonstrates that the wave description applies even when individual particles are detected one by one. The rules of quantum mechanics use mathematical equations to predict how wave functions behave. The equations are tools that give numbers for probabilities and for average values. Using these equations, scientists can calculate the expected distributions of results for many kinds of experiments. The math can also predict average energies, average positions, and average momenta of systems under given conditions. The concept of allowed energy levels comes from the wave description when a particle is held in a region by forces. In such situations, only certain standing patterns of the wave function can exist. Each standing pattern corresponds to an allowed energy. The mathematical rules select these patterns. The allowed energies and the shapes of the standing patterns determine many physical properties of atoms and molecules. Quantum mechanics also gives rules for how particles behave when they are free to move over large regions. In free motion, the wave function can spread out or travel in space. The probability to find a particle in a given region can change in time according to the rule that governs the wave function. The spreading or motion of the wave function leads to measurable effects in scattering experiments. In those tests, incoming particles interact and then move away. Scientists record where the outgoing particles go and what energies they carry. Comparing those records with the predictions from the wave function helps to test and refine the theory. Measurement has a special role in quantum mechanics. Before a measurement, the wave function may provide several possible outcomes with different probabilities. When the measurement is made, one outcome is found. The result that appears is not controlled with certainty in most cases. It appears with a probability given by the wave function. After the measurement, The system is found in the state that corresponds to the measured outcome. A measurement can also change the wave function and the possible outcomes that will appear in a later measurement. The act of measuring updates the description of the system. This updating is part of how quantum mechanics links the predictions from the wave function to actual experimental records. It is important to note that the measurement process requires an interaction between the system and an instrument. The instrument records a definite result. The rules tell how to connect the recorded result to the prior wave function and how the description changes after the result. Quantum mechanics also accounts for quantities that are conserved in processes. Energy is conserved overall. Momentum is conserved overall. Electric charge is conserved in interactions. The wave function and the rules preserve these conservation laws. When scientists calculate possible outcomes for a reaction or a decay, they use the conservation laws to eliminate impossible outcomes. This helps to predict which processes can happen and which cannot. Particles have discrete properties that the wave description uses. Spin is one of those properties. Spin is a basic quality of a particle that affects how it can be arranged with other particles. The wave description includes spin and treats it as part of the state. Energy, charge, and spin all enter into the rules that govern allowed states and transitions. Quantum theory also handles systems of many particles. When particles are combined, the overall wave function describes the joint possibilities for all the particles. In systems with many identical particles, the wave description includes rules that tell how the overall state can be formed. These rules lead to important differences between particles that are fermions and particles that are bosons. The rule for fermions limits how many particles can occupy the same state. The rule for bosons allows many particles to share the same state. These basic rules shape the properties of matter and of forces at larger scales. The predictions of quantum mechanics are tested in many kinds of experiments. Measurements of atomic spectra confirm the discrete energies of electrons in atoms. Measurements of scattered particles confirm the wave nature of motion. Tests that record many individual events show the statistical patterns predicted by the wave function. The agreement between calculations and experiments is strong in many cases. Where calculations and data differ, scientists refine the models or build new experiments to find the source of the difference. Quantum mechanics uses probability rather than certainty in many predictions. This probabilistic aspect is not due to poor instruments in most cases. It is built into the rules that describe small-scale systems. When scientists repeat identical experiments many times, the distribution of results follows the probabilities given by the wave function. From those distributions, scientists can compute averages and uncertainties. Those averages often match the stable values seen in measurements of macroscopic systems. Even though the rules include probability, the math gives very precise numerical predictions. The equations allow the calculation of precise probabilities for many experiments. That precision is why quantum mechanics is a powerful tool. Scientists use the predicted probabilities to design instruments and to interpret data. The quantitative nature of the predictions makes it possible to test the theory in specific ways in laboratories and in observations. There are different ways that people describe what the wave function means. Some descriptions focus on the role of the wave function as a tool for predicting measurement outcomes. Other descriptions try to give a physical interpretation of the wave function itself. These discussions are part of the broader study of the meaning of quantum mechanics. The practical use of the theory, however, relies on the equations and the link between the wave function and measured results. The wave description also explains why some processes occur only at set energies. When a photon is emitted or absorbed, its energy matches the difference between allowed energies. This fact explains why atoms show lines at certain energies in their spectra. It explains the behavior of lasers and other devices that use precise energy transitions. The control of electron transitions is the basis for many applications that depend on light emission and absorption. In problems where particles move under the influence of forces, the wave function gives the patterns of probability for motion. Those patterns determine the expected outcomes for experiments that measure position or momentum or energy. The mathematical rules allow for the calculation of these patterns and their evolution in time. The results can be applied in many practical situations where precise control or prediction of microscopic behavior is needed. Quantum mechanics also addresses the idea of measurement devices. Instruments are physical systems that interact with the system under study. A proper description of the full process includes the wave function of the system and the wave function of the instrument. In practice, scientists use methods that treat the instrument as producing a definite record. The theory gives rules for how to link the prior probabilities to the recorded outcome and to the post-measurement state. The wave description replaces certainty about some single property with a set of probabilities for different possible values. That change in viewpoint is central. It changes how scientists think about processes at the smallest scales. It also gives the tools to compute what detectors will record and how often they will record certain results. These tools are at the heart of modern particle physics and of technologies that rely on the behavior of small systems. The ideas presented here show that particles at small scales must be described with wave functions and probabilities. They explain the discrete energies seen in atoms and the emission and absorption of photons. They explain how patterns arise from the addition and subtraction of wave probabilities. They show how measurement updates the description to give single results. The notion that a particle can be described by many possible outcomes with set probabilities is a central idea. This idea that a particle can be in several possible states at once is the core of superposition and the special role of measurement. Superposition means a particle can be described by several possible states at once. The wave description gives many possible outcomes and a number for each outcome. Those numbers set the chances for each result when we measure the particle. This idea is the heart of how we predict what a particle will do in an experiment. A superposition is a state that combines other states. Each possible state in the combination has a number attached. That number is called an amplitude. To find the chance to get a given result, we take the square of the amplitude. If the amplitude for a result is large, the chance is large. If the amplitude is small, the chance is small. The sum of the chances for all possible results is always 1. Superposition applies to many properties. A particle can be in a superposition of different places. A particle can be in a superposition of different energies. A particle can be in a superposition of different spin values. For example, an electron can have a state that gives some chance to be near one region and some chance to be near another region. A single measurement will find the electron at one position. Repeating the same experiment many times under the same conditions gives a set of positions. The pattern of positions matches the probabilities given by the wave description. When a particle is in a superposition of energy states, a measurement of energy gives one of the allowed values. If the amplitudes give equal chances for two energy values, half of the measurements will give one value and half will give the other over many trials. The precise fraction can be found by counting outcomes when the experiment is repeated many times. That statistical pattern is what the wave description predicts. Spin shows superposition clearly. Many particles have a spin of 1/2. For such a particle, a measurement of spin along a chosen direction gives one of two results. We call those results spin up and spin down for that direction. A particle can be prepared in a state that is a superposition of spin up and spin down. If the amplitudes are equal, the chance to measure spin up is 1/2, and the chance to measure spin down is 1/2. A single measurement gives one definite answer. Repeating the measurement many times gives the statistical pattern that the wave description predicts. The act of measuring is not a passive observation. A measurement involves an interaction between the particle and the instrument. The instrument is built to record a particular property. When the instrument interacts with the particle, it records a definite value. That recorded value is one of the allowed outcomes for the instrument. After the interaction, the particle is found in the state that corresponds to the recorded value. In other words, the measurement updates the description of the particle to match the result that was recorded. If no other changes occur between two measurements of the same property, repeating the same measurement soon after the first will give the same result. This is because the first measurement left the particle in a state that yields that result with certainty. If, however, something changes the particle between the two measurements, the second measurement can give a different result. Measuring a different property in between can change the state and thus change the outcome of the later measurement. Different properties can be incompatible in the sense that measuring one can affect the other. A precise measurement of one property can make the other property less definite. This is not only a limit of the instruments, it is a rule about how properties behave at the small scale. Measuring one property changes the state, and that change affects what can be known about other properties afterward. The wave description lets parts of the description add or subtract. When parts add, the chance to get a result can increase. When parts subtract, the chance can decrease or even go to zero. This addition and subtraction of parts is called interference. Interference shows that the different possibilities in a superposition can act together to change the probabilities. The pattern of outcomes in many repeated trials shows the interference that the wave description predicts. Interference appears in many situations. If a particle has two main possible ways to get to a detector, the two parts can interfere. The interference changes where the detector is most likely to record the particle. If the instrument learns which way the particle took, the interference disappears because the act of learning changes the state. When no information is recorded about the way, the interference can remain and affects the distribution of outcomes. Preparing a superposition requires control. Scientists use fields, pulses, or interactions to place a particle into a state that combines other states. For example, a short pulse of light can move an electron in an atom into a combination of two energy states. A magnetic field can rotate the spin state of a particle and make it a superposition of spin up and spin down. The methods differ with the system, but the idea is the same. Use a controlled interaction to set the amplitudes for the desired possibilities. A useful point is that the phases of the amplitudes matter. The amplitudes carry more information than their squares. The relative signs or phases between amplitudes determine how the parts add or subtract. When the phases are stable, interference can appear. If the phases change or become random, interference is lost. The presence or absence of interference depends on the relation between amplitudes, not only on their sizes. When a system interacts with many other degrees of freedom, the relative phases can become scrambled. This process is called decoherence. Decoherence reduces or removes interference. After decoherence, the description looks like a mixture of definite outcomes with certain chances. The mixture does not show the interference that a coherent superposition shows. In practice, decoherence explains why macroscopic instruments and everyday objects behave in a way where one definite outcome appears stable. The difference between a coherent superposition and a mixture is important. In a coherent superposition, the parts keep a definite relation that can produce interference. In a mixture, that relation is absent or unknown. If we have a single particle in a superposition, we can arrange tests that reveal interference. If we have many particles, where each is in one definite state but we do not know which, interference does not appear. The wave description tells us when we can see interference and when we cannot. Probability is central. Quantum rules give the chance for each result. The outcome of a single measurement is often random within those chances. Randomness here means that the exact result cannot be predicted with certainty before the measurement. The key is that the probabilities are well defined. When the same experiment is repeated many times, the pattern of results follows the predicted probabilities. That makes the theory testable and useful. Scientists compare the counted outcomes with the calculated probabilities to check the validity of the model. Counting outcomes requires careful experiments. When the predicted chance for a result is small, many trials may be needed to see that result enough times to estimate its probability accurately. Scientists design experiments to reduce false signals and background effects. They repeat experiments and collect data. The process of collecting many events and comparing with probabilities is the standard way to test and confirm the rules about superposition and measurement. Some measurements are destructive. For example, detecting a photon often means the photon is absorbed and its energy is transferred to the detector. The photon is not available for later measurements of the same type. Other measurements can leave the particle available for later tests. The nature of the interaction between the system and the instrument determines what happens after the measurement and what can be measured next. A measurement has a set of possible answers it can give. These answers are the allowed outcomes of that measurement. Preparing the instrument defines which set of answers it will give. Different instruments can be built to measure different properties. The instrument must interact with the system in a way that links the property to a record. The design of the instrument affects what is measured and how the state changes during the interaction. The concept of an eigenstate is a way to name a state that gives a definite outcome for a particular measurement. If a particle is in an eigenstate of a measurement, measuring that property will give the corresponding result with certainty. After such a measurement, the particle remains in that eigenstate if the measurement is repeated and no other process changes it. Preparing eigenstates is a common goal in experiments that need reliable results. Superposition also applies to systems of several particles. Two or more particles together can have a joint state that is a superposition of joint possibilities. In such cases, the parts of the superposition can link the particles so that the outcome for one particle is tied to the outcome for the other. This linking is a form of superposition that involves more than one particle. When particles are linked in this way, measuring one affects what we can say about the other. The linked states of several particles are the basis of entanglement. Entanglement means that the joint state of the particles cannot be written as a simple product of individual states. Instead, the overall state must be described together. If two particles are entangled, measuring a property of one gives information about the outcome of a measurement on the other, even if the particles are separated by a large distance. This linking is a direct consequence of superposition in systems with many parts. Entanglement has practical uses and also deep implications. In applications, entanglement can be used to correlate outcomes across distance. In experiments, entanglement tests show that the statistical patterns of linked results follow the quantum rules and cannot be explained by simple local hidden variables. The tests rely on preparing entangled states and measuring correlations across many trials. The time evolution of superpositions is another important feature. The amplitudes change in time according to the rules that govern the system. When amplitudes for different states have different energies, the relative phases evolve in time. That evolution can make interference patterns change. For example, a superposition of two energy states can produce oscillations in properties as time passes. Measuring at different times can give different distributions of outcomes because the amplitudes and their relative phases change. Superposition is used in many devices and ideas. In one application, quantum bits or qubits use superposition of two states to store information. While a classical bit holds either 0 or 1, a qubit can be in a superposition of 0 and 1. Measurement of the qubit yields either 0 or 1 with the probabilities set by the amplitudes. Many repeated runs are used to extract information from qubits and to perform computations that depend on quantum interference between many states. The practical use of superposition in devices depends on the ability to prepare states, to control their evolution, and to measure them reliably. Keeping superpositions coherent can be hard. Interactions with the environment, with uncontrolled fields, or with stray particles can cause decoherence. Loss of coherence reduces the usefulness of superposition for interference and for quantum tasks. Engineers and scientists work to isolate systems and to use error control methods to maintain coherence long enough for a device to perform its function. Superposition also affects how we interpret measurements and records. Instruments are macroscopic systems made of many particles. When a small quantum system interacts with a large instrument, the combined system evolves into a state where different outcomes correspond to different states of the instrument. Because the instrument has many parts and because it interacts with its environment, the different outcome records become stable and do not show interference. That is why instruments give single recorded values that observers can read off and use. People have different ways to describe how a single definite outcome appears from the underlying superposition. Some descriptions focus on the practical rules that link the wave description to recorded outcomes. Others explore the deeper meaning of how a definite result appears from possibilities. For practical work, the focus stays on the rules that predict the probabilities and on how instruments record outcomes. Those rules are what experiments test and what engineers use to make devices. The basic steps in a typical experiment are clear. First, prepare the system in a known state. Second, let the system evolve or interact. Third, measure a chosen property with an instrument. Fourth, record the outcome. Fifth, repeat the whole procedure many times to build statistics. From the recorded frequencies, compare with the probabilities that the wave description predicts. This sequence is the standard way to connect the superposition idea with observed data. Superposition shows that the particle description before measurement often includes many alternatives. Measurement makes one definite alternative appear in the record. The pattern of many such definite records matches the probabilities given by the wave description. The act of measuring changes the state and sets the system into the measured form. The evolution between measurements and the interactions that occur determine how the probabilities change in time. Because superposition applies to many systems, a wide range of phenomena follow from it. Some effects that arise from superposition include particles appearing on the far side of a barrier, linked outcomes for separated particles, and limits on how precisely certain pairs of properties can be known at the same time. These effects all come from the same basic idea. The wave description gives many possible outcomes, and the measurement process selects one outcome in a way that follows set probabilities. From the ideas of superposition and measurement come three striking effects: tunneling, entanglement, and the uncertainty principle. These effects show how particles can act in ways that are different from everyday expectations. Each effect follows the rules of quantum mechanics and has been tested in careful experiments. Each effect also matters for real devices and for our understanding of nature. Tunneling is a process where a particle can appear on the other side of a barrier. The wave description of a particle gives a probability for where the particle may be found. Even when the probability is very small inside and beyond a barrier, it may not be zero. That non-zero probability means the particle can be found on the far side of the barrier. When this happens, we say the particle tunneled through the barrier. A barrier is a region where the chance to find the particle is low. The barrier can be a region where the potential energy is higher than the particle has as average energy. The wave part of the particle extends into the barrier. The wave can be small in the barrier. The wave can also extend past the barrier. The amount of wave that reaches the other side sets the chance for the particle to appear there. The chance to tunnel depends on the height and the width of the barrier. A higher or wider barrier makes the chance smaller. A lower or narrower barrier makes the chance larger. The mass of the particle and the energy of the particle also affect the chance. Heavier particles or lower energy give smaller chance. Lighter particles or higher energy give larger chance. Tunneling shows up in many processes. One clear case is nuclear alpha decay. Some heavy nuclei emit an alpha particle. The alpha particle is a bundle of 2 protons and 2 neutrons. Inside the nucleus, the alpha particle is held by a barrier made by the strong force and by the electric force. The alpha particle does not have enough energy to climb over the barrier. Still, an alpha particle can appear outside the nucleus by tunneling. The measured rates of alpha decay match the probabilities predicted by the wave description. Tunneling also appears in electronic devices. When 2 conductors are very close but separated by a thin insulating layer, electrons can move across the gap by tunneling. This motion produces a measurable current. Devices that use this effect include tunnel diodes and scanning tunneling microscopes. In a tunnel diode, the current can change with applied voltage in a way that engineers use to make amplifiers and oscillators. In a scanning tunneling microscope, a very sharp metal tip is placed near a surface. As the tip moves, the tunneling current changes. Measuring that current as the tip scans gives a map of the surface at atomic scale. Tunneling plays a role in chemical and biological processes as well. Electrons can tunnel in some chemical reactions. In some cases, the motion of an electron by tunneling changes how a reaction proceeds. Tunneling also helps explain how protons and other light particles move in specific chemical environments. In stars, tunneling helps fusion occur at the temperatures that stars have. Nuclei repel each other because they have positive electric charge. To fuse, they must come very close, so the strong force binds them. In many cases, their energy is not high enough to overcome the electric repulsion classically. Tunneling gives a finite chance that the nuclei can be found close enough to fuse. This tunneling effect helps sustain the reactions that make the star shine. Tunneling is not a rare curiosity. It is a quantum rule that operates when probabilities and wave behavior are important. Engineers and scientists use tunneling in devices and in theory. The effect shows that the wave description can give outcomes that are not allowed by a simple particle path idea. Entanglement is a different kind of quantum effect. Entanglement means the full description of 2 or more particles must treat them together. The state of the whole system cannot be split into separate states for each particle. When particles are entangled, measuring one particle gives information about what will be found when the other particle is measured. A simple case is 2 particles created in a process that conserves total spin. If the total spin is set to 0, the 2 particles must have opposite spin results along any chosen direction. The individual outcome for each particle is random when measured, but the outcomes are correlated. When one shows spin up, the other shows spin down for the same measurement direction. That link between outcomes holds even when the particles are moved far apart after they are created. Entanglement produces correlations that are stronger than those allowed by models that assume each particle carries a preset answer for every measurement. Scientists have tested such models by preparing many pairs of particles and measuring them in different ways. The measured correlations follow the predictions of quantum mechanics and cannot be explained by simple models that rely only on local preset values. The outcomes of individual measurements are random. Entanglement does not let a person control the outcome on one side to send a message to the other side instantly. To see the correlation, people must compare results by ordinary communication, which does not travel faster than light. The statistical pattern of many trials reveals the link. The link shows that the particles share a joint quantum state until they are measured. Scientists create entangled pairs in several ways. Some decays produce two entangled particles. Optical devices called nonlinear crystals can produce pairs of entangled photons by a process called parametric down conversion. Trapped atoms and ions can be manipulated to form entangled states. Superconducting circuits can also form entangled states for electrons and Cooper pairs. Many experimental platforms now produce entanglement with high control. Entanglement has practical uses. It can improve the security of communication. In quantum cryptography, entangled pairs can reveal when an eavesdropper tries to intercept the signals. Entanglement also appears in quantum computing methods. In some algorithms, entangled states let a device process certain patterns of possibilities more effectively than if the parts were independent. Entanglement also aids high-precision measurements in some sensors. The uncertainty principle sets limits on what we can know about pairs of properties of a single particle. For certain pairs of properties, such as position and momentum, the more precisely we know one, the less precisely we can know the other. This rule is not a limit of instruments alone. It is a fundamental property of quantum states. Position and momentum are a common pair. Position tells where the particle is located. Momentum tells how the particle moves and how hard it is to change its motion. If the wave description assigns a very narrow range of positions to the particle, then the values of momentum that are consistent with that narrow position cover a wide range. If the wave description assigns a narrow range of momenta, then the positions that match that momentum cover a wide region. This trade-off is the core of the uncertainty principle. The uncertainty principle appears in time and energy as well. A state that lasts only a short time has a less definite energy. Conversely, a state with a very well-defined energy tends to last a long time. This relation explains why short-lived excited states of atoms and of nuclei produce a spread of photon energies. The spread shows as a broadening of spectral lines. Long-lived states give narrow spectral lines. The uncertainty principle affects measurements. A precise measurement of position involves an interaction that produces a state with limited position spread. That state will have a wide range of allowed momenta. A later measurement of momentum will then show a wide spread of values. The principle makes it impossible to ascribe definite values for both properties at the same time beyond the limits set by the rule. Uncertainty and tunneling are connected. When a particle is confined in a small region, its momentum uncertainty can be large. That large uncertainty means the particle can have momentum values that allow it to be found beyond a barrier. In other words, the wave description and the uncertainty principle together allow some probability for tunneling events. Entanglement and uncertainty also interact. For entangled particles, measuring one particle can reduce the uncertainty about a corresponding property of the other particle. For example, if two particles are entangled so their positions are strongly correlated, measuring the position of one can tell us about the likely position of the other. Still, the uncertainty principle applies to each particle's complementary properties. Even with entanglement, the trade-off between position and momentum remains for individual measurements. All three effects are tested in experiments. Tunneling is measured in nuclear decay rates, in electronic tunnel currents, and in surface imaging methods. Entanglement is tested by producing many entangled pairs and measuring correlations under varied settings. The key tests compare the measured correlations with the limits set by classical or local models. The experiments show that quantum rules hold. The uncertainty principle is tested by measuring position and momentum distributions and by measuring spectral widths of short-lived states. A simple experimental pattern for entanglement tests goes as follows. First, prepare many pairs in an entangled state. Second, measure a chosen property on each particle of a pair. Third, record the pair of outcomes. Fourth, repeat the process many times while changing the measurement settings. Fifth, compare the recorded pairs across the different settings. The pattern of the correlations shows whether the outcomes follow the quantum predictions or not. Tunneling experiments also follow a clear pattern. For alpha decay, physicists measure how often the decay happens and what particles appear. The measured decay rates match the calculated probabilities from the wave description and the barrier properties. For tunnel diodes and scanning tunneling microscopes, engineers measure current as a function of voltage or tip position. The observed currents match models that include tunneling as the mechanism for electron flow. The uncertainty principle is visible in measurements of spectral lines and in diffraction experiments. If a beam of particles passes through a narrow slit, the distribution of angles after the slit is broad. The narrower the slit, the broader the range of angles. Counting many particles and recording their angles shows the spread and confirms the trade-off between position and momentum details for the beam. Tests of entanglement have been performed with particles separated by large distances. In some experiments, the two measuring stations are placed far enough apart that a signal traveling at the speed of light could not carry the setting choice from one station to the other during the time between the measurements. The measured correlations still match quantum predictions. Scientists interpret these results to mean that the correlations are not explained by simple local instructions carried by each particle before the measurements. All three effects play a role in technology. Tunneling is used to make sensitive microscopes and some electronic components. Tunneling helps control currents in small devices. Entanglement is an active tool in secure communication and in research toward quantum computers. The uncertainty principle guides what measurements can do and how precisely devices can resolve pairs of properties. Understanding these effects requires careful experiment and clear analysis. Experiments must control conditions, reduce unwanted interactions, and record many trials. For entanglement tests, experiments must ensure that the measurements are independent and that results are recorded reliably. For tunneling and uncertainty tests, experiments must measure distributions and account for background effects. Scientists use statistics to compare the recorded frequencies with the predictions of quantum models. The study of tunneling, entanglement, and uncertainty also raises deep questions about the meaning of quantum states and measurements. People discuss how definite outcomes appear from the wave description and how the measurement process should be described in full detail. These are active topics in both experiments and theory. At the same time, The practical rules that link wave descriptions to measured probabilities work well in predicting experimental outcomes and in guiding the design of devices. The reality of these effects rests on data. Repeated experiments with independent setups and independent teams confirm the predictions of quantum mechanics. The measurements match the calculated probabilities and the expected patterns of correlation and spread. Where experiments disagree with predictions, scientists examine the data and refine the tests or the models. This careful process builds confidence in the results. These effects are not just theoretical ideas. They are real processes that affect how particles behave and how devices operate. Scientists use tunneling to probe surfaces and to build components. They use entanglement to test the limits of quantum rules and to try new kinds of communication and computation. They use the uncertainty principle to set limits and to guide measurement design. Tunneling, entanglement, and uncertainty are linked by the same quantum foundations. Superposition makes entanglement possible. Superposition and the wave nature make tunneling possible. The wave description and the mathematics of quantum mechanics give the uncertainty limits. Each effect shows a different face of how matter behaves at the smallest scales. Many experiments explore these effects in detail. They measure decay rates, currents, correlations, and distributions. They test the predictions under changing conditions. The results have practical and theoretical value. They show how the quantum rules apply and how we can use them in devices and in further study. The knowledge built from these tests helps to design new tools. It helps to refine theories and to suggest new experiments. By measuring and comparing, scientists increase what they know about particles and their interactions. This process of careful testing and analysis is central to the study of matter at the smallest scales. Understanding tunneling, entanglement, and uncertainty gives a deeper view of the quantum world. These effects explain how particles can appear where they might not be expected, how distant particles can show linked outcomes, and how certain pairs of properties cannot be known at once beyond a set limit. Together, these ideas shape the behavior of atoms, nuclei, and the particles that make them. Many careful experiments confirm these principles and continue to test their limits. Scientists use careful tests to show how particles behave. Some experiments are simple to describe. Some are more complex. Each experiment gives facts that help us trust the rules of quantum mechanics. This chapter explains the most important experiments in plain words. It shows what each test measures. It shows what the results mean. The double-slit test shows wave behavior and the role of measurement. The setup uses a source that sends particles toward a barrier with two narrow slits. Behind the barrier is a screen that records where particles arrive. The source can send particles one at a time or many at once. When the source sends many particles, the screen shows a pattern of many hits. That pattern has bright and dark stripes. The pattern is called an interference pattern. The pattern appears even when particles are sent one at a time. Each hit on the screen is a single event. Over many events, the interference pattern builds up. The result tells us that the description of each particle must include parts that add or subtract probabilities. If an instrument is placed at the slits to record which slit a particle passes through, the interference pattern disappears. In that case, the screen shows a pattern expected from particles that go through one slit or the other. The act of getting which way information changes the possible outcomes. The double-slit test, done with light, electrons, atoms, and even molecules, gives clear evidence for superposition and for the role of measurement. The photoelectric test shows the particle nature of light. In this test, light shines on a metal surface. The metal can emit electrons when struck by light. The number of emitted electrons and their energies are measured. The experiment changes the color of the light and its brightness. The result shows that there is a minimum color or frequency of light needed to emit electrons from that metal. Below that color, no electrons appear, no matter how bright the light is. Above that color, electrons appear and their maximum energies grow with color. The brightness changes the number of emitted electrons, but not their maximum energies. These facts led scientists to say that light comes in packets of energy. Each packet carries an amount of energy proportional to the color. The packets are called photons. The photoelectric test supports the view that light has particle properties that matter in interactions with matter. Electron diffraction experiments show that electrons have wave properties when they move. In one classic test, a beam of electrons strikes a crystal. The electrons that emerge form a pattern on a detector. The pattern is the same kind of pattern that beams of waves give when they scatter from a regular array of obstacles. The measured pattern matches the predictions of the wave description for electrons. Other tests send electrons through narrow slits. These tests produce interference patterns on a screen. The patterns depend on slit spacing and on electron energy in the way that wave rules predict. These experiments show that the motion of electrons must be described by a wave description in many situations. Atomic spectra experiments record the light that atoms give off or absorb. When atoms change their electron energies, they emit or absorb photons of specific colors. Scientists measure these colors with instruments that spread light by frequency. The recorded lines form a pattern that is specific to each kind of atom. The pattern gives the precise differences between allowed energies in the atom. Repeated measurements give the same lines. The measurements show that electron energies in atoms are discrete. Spectroscopy also lets scientists measure other properties, such as small shifts in energy due to fields or to nuclear effects. Spectral lines provide a fingerprint for elements. They help to build the models of atomic structure and to test quantum rules. The Stern-Gerlach test shows quantization of spin. In this experiment, a beam of atoms passes through a magnetic field that is not uniform. The beam splits into a set of separate paths. For atoms with a certain electron arrangement, the split shows two or a few separate outcomes. The measured spots on a detector appear at discrete positions. The result means that the measured property, spin along the chosen direction, can take only certain values. The test also shows that measuring spin along one direction can change the results for a later measurement along a different direction. The Stern-Gerlach test is a direct demonstration that some properties are quantized and that measurement sets the state. Experiments that test entanglement use pairs of particles created together. The pairs are prepared so that the joint state has a specific property. For example, their total spin may be fixed to a certain value. The two particles travel to separate stations. At each station, a measurement device records a chosen property. The choice of what to measure can be made randomly and at the last moment. The recorded pairs of outcomes are collected. The patterns of outcomes show correlations that follow quantum rules. The correlations can violate limits that any model based only on local preset values would obey. Scientists call these tests Bell tests. The experiments measure many pairs under many settings. The results match the predictions of quantum mechanics and disfavor simple local hidden variable models. Later versions of the tests closed technical loopholes. The overall set of tests gives strong evidence that entangled particles share a joint quantum state that produces correlated outcomes when measured. Compton scattering experiments probe the particle properties of light and momentum transfer. In these tests, X-rays strike electrons in a material and scatter. The scattered X-rays are measured in direction and in energy. The measured change in energy of the scattered X-rays matches the calculation for a collision between a photon and an electron in which energy and momentum are conserved. The result gives direct evidence that photons carry energy and momentum in particle form when they interact with electrons. Tests of tunneling include measurements of nuclear decay and measurements in solid matter. In alpha decay experiments, scientists measure how often heavy nuclei emit alpha particles. The measured decay rates match the probabilities calculated from the wave description and the barrier properties. In electronic systems, experiments measure currents that flow across thin, insulating layers. The presence of a current in conditions where a classical path is forbidden shows that electrons can be found on the far side of a barrier by quantum rules. Devices such as the scanning tunneling microscope record tunneling currents as a fine tip moves near a surface. The measured currents change sharply when the tip moves a small distance. These measurements give direct evidence for tunneling on atomic scales. Tests of the uncertainty principle use diffraction and spectral width measurements. A beam of particles sent through a narrow slit spreads out in angle. The narrower the slit, the broader the range of outgoing angles recorded on a screen. This spread is a direct effect of the wave description and of the trade-off between position range and momentum range. In atomic spectroscopy, short-lived excited states emit photons whose energies show a spread. The shorter the lifetime of the state, the broader the measured energy distribution. The observed spreads obey the quantitative rule that links time and energy uncertainty. These measurements confirm that certain pairs of properties cannot be known simultaneously with arbitrary precision. Many experiments use detectors that record single events and store them for later analysis. Early detectors included photographic plates and cloud chambers. Photographic plates recorded tracks of charged particles as marks. Cloud chambers made tracks visible as a trail of condensed vapor. Bubble chambers used a liquid that forms visible bubbles along the path of a charged particle. Later, detectors used electronic sensors that give fast signals and allow precise timing. Over time, detectors became more sensitive and faster. Modern detectors include semiconductor sensors that record charge deposits, light sensors that record the photons produced by particles, and arrays that collect signals over a large area. Detectors are chosen for the property that needs to be measured, such as energy, charge, time, or position. Counting and statistics are central to all tests. Single detections give definite results. Repeating the same test many times produces a set of results. Scientists count how often each outcome appears. They compare the counted frequencies with the probabilities predicted by quantum rules. To test a theory, the experiment must collect enough events to make a reliable comparison. Experiments also measure and subtract background signals that come from sources other than the process of interest. Calibration runs and control experiments test that the instruments work as expected. The careful use of statistics makes it possible to decide whether the observed patterns agree with the predictions. Many experiments were repeated by different teams and with different instruments. Independent verification is important when different groups measure the same effect with different setups and find the same agreement with the theory. Confidence grows in the result. Where experiments gave unexpected results, other teams repeated the tests with improved control. That process of checking and repeating is a core part of experimental science. Some classic experiments led to major shifts in the understanding of matter. Tests that probed atomic structure and light-matter interactions gave the evidence needed to build quantum models. Tests of entanglement challenged the idea that particles carry only local preset values. Tests of tunneling and of discrete energy levels explained many nuclear and chemical processes. Each experiment gave a piece of the full picture. The combined results built the framework scientists now use to describe the small-scale world. Experimental progress depends on tools and on careful design. Some tests need isolated systems where stray interactions are reduced. Other tests need high event rates and fast detectors. Some tests need high-energy inputs to produce rare particles or to probe small distances. The choice of tools follows what property is being tested and how precise the measurement must be. Advances in instruments often open the door to new tests and to the discovery of new particles. The record of experiments includes both simple tabletop setups and large facilities. Small experiments can show basic quantum effects in accessible ways. Large facilities provide high energies and large data samples for detailed tests. In large facilities, teams of engineers and scientists design beams, detectors, and data systems to run long experiments. The combined human and technical effort is organized to collect and to analyze the data in a reliable way. Key experiments also show the role of control and timing. In tests of entanglement, the choice of measurement settings must be made at the right time to ensure independence. In fast decay measurements, detectors must record times with high precision. In interference tests, the stability of the setup and the coherence of the sources determine whether interference is visible. Controlling these factors requires careful planning and precise instruments. The findings from these experiments are both practical and conceptual. They give the numbers needed to design devices and to build models. They also give direct facts about how particles behave. The tests show that the wave description gives correct probabilities. They show that superposition, tunneling, entanglement, and uncertainty are real effects that apply in many systems. The results guide the building of both theories and technologies. Many modern experiments use beams of particles that are prepared, guided, and measured. The beams are often produced and shaped by machines that speed up charged particles and send them to targets or to collide them with other beams. Detectors surround the interaction regions and record the particles that appear. Data systems store large numbers of events for later study. The combination of beams and detectors lets scientists test particle properties at energies and at event rates that small setups cannot reach. Experiments continue to test the limits of the theory. New tests try to measure tiny deviations from predicted values. Some tests search for new particles that would show up as unexpected signals. Other tests push to higher precision in known effects. The steady cycle of proposing tests, building instruments, taking data, and analyzing results is how the field advances. From the simple double-slit test to complex searches for new particles, experiments are the link between ideas and facts. The record of experiments gives the solid basis for the quantum description of small systems. To go further, scientists use beams and detectors that can reach new energies and record more detail. These tools let them explore how particles interact and how new particles can appear in high-energy processes. To study the collisions and the new particles that appear, scientists build machines to push particles and instruments to record what happens. These machines are particle accelerators. The instruments are detectors. Accelerators give particles high energy. Detectors record the tracks and the energies of the particles that appear. Together, they let scientists turn an invisible process into data that can be measured and studied. An accelerator uses electric fields to speed up charged particles. The fields push the particles and increase their energy. In many machines, the fields are repeated in a set of cavities. Each pass through a cavity adds more energy. In linear accelerators, the particles travel in a straight line and pass once through a series of accelerating gaps. In circular accelerators, the particles travel around a ring and pass many times through the accelerating cavities. Magnets bend the path and keep the particles on the desired orbit. Magnets do more than bend. Some magnets focus the beam and keep it tight as it moves. Other magnets steer small corrections to the path. The machine must keep the beam inside a vacuum pipe. The high vacuum reduces collisions with air molecules. If the beam hits gas, particles can be lost or unwanted signals can appear. The vacuum and the magnets together let the beam reach very high energies. Different accelerators are suited to different tasks. A linear machine is good when the beam will be used once or when it is hard to bend the particles. A circular machine is efficient when the beam can be reused many times. Circular machines can reach high energies by adding a little energy each turn. But when a charged particle moves on a curved path, it can lose energy as radiation. That radiation is stronger for light particles and for tight curves. Engineers must design the machine to balance these effects. Two general collision setups exist. In a fixed target setup, a beam hits a stationary target. In a collider setup, two beams travel toward each other and collide head-on. A head-on collision concentrates the available energy at the collision point. That concentration helps to create heavy new particles. Fixed target experiments often produce many events and are useful for certain measurements. Colliders give access to higher center of mass energy for given beam energies. The energy in a collision can become matter. If enough energy is present, new particles can appear. The heavier the particle we want to produce, the more energy we need. Collisions also produce many lighter particles. Scientists search the resulting debris for patterns that match the expected signals of a new particle. They use conservation rules, such as conservation of energy and of electric charge, to help reconstruct what happened. A detector records the results of collisions. Detectors are layers of instruments arranged around the collision point. Each layer measures a different property. The innermost layers measure where charged particles pass by. The next layers measure the energy carried by particles. The outer layers identify particles that penetrate through the inner parts. A magnetic field usually runs through the detector to bend the paths of charged particles. The curvature tells the momentum of a charged particle. Tracking detectors sit close to the interaction point. They record precise positions where charged particles pass. Modern tracking often uses silicon sensors. Tiny silicon pixels record a charge when a particle crosses. The pattern of hits builds a track that shows the particle path. High-precision trackers can tell where the collision took place. They can also separate tracks that come from different closely spaced collision points. Gas detectors use a different method. When a charged particle crosses a gas volume, it ionizes the gas. The free electrons drift to collection wires or to readout pads. The arrival time and the position of the signal give information about the particle path. Drift chambers and wire chambers were widely used for many years. They still appear in many experiments where large volumes are needed at reasonable cost. Calorimeters measure energy. An electromagnetic calorimeter measures the energy of electrons and photons. A hadronic calorimeter measures the energy of protons, neutrons, pions, and other hadrons. When a high-energy particle enters a calorimeter, it produces a cascade of secondary particles that deposit energy in the detector material. Sensors collect the deposited energy and give a signal proportional to the total energy. Calorimeters can be built as layers of dense absorber and active material. The absorber makes the particle shower, while the active layers record the deposits. Muon detectors lie at the outer layers. Muons are charged particles that pass through calorimeters more easily than many other particles. Because muons penetrate farther, detectors placed outside the calorimeters are designed to record them. These outer detectors use gas tubes or scintillator counters. A muon that passes through the entire detector leaves hits in the outer system. These hits, combined with the inner track, show that the particle was a muon. Particle identification uses several measurements. The curvature of the track gives momentum. The energy deposit in a calorimeter gives energy. For charged particles, the energy loss per distance traveled gives clues about the particle mass at a given momentum. Time of flight measurements give the particle speed. Cherenkov detectors measure light produced when a particle moves faster than light travels in that medium. Combining momentum and speed allows a mass estimate. Transition radiation detectors help to distinguish electrons from heavier particles at high energies. Detectors must operate fast. Collisions in a high-energy machine can occur at very high rates. The raw data from every collision would be too large to store. Detectors use trigger systems to decide which events to record. The first stage of the trigger is usually hardware-based. It looks for simple patterns and reduces the event rate quickly. Later stages use software to run more complex selections. The goal is to keep the interesting events and discard the routine ones in real time. After the triggers choose an event, the data acquisition system gathers signals from many detector elements. The system builds a coherent record for each selected collision. The data are stored and later analyzed. Modern experiments record millions or billions of selected events. Computers and networks move and store the data. Scientists use software to reconstruct tracks, clusters, and to identify particles. Calibration and alignment constants are applied to make the measurements precise. Large detectors require careful calibration. The response of sensors can change with time and with operating conditions. Scientists use known signals to adjust the response. For example, they use particles with known energies or signals produced by dedicated calibration systems. Detector alignment uses tracks from particles to map the relative positions of sensors. Good calibration and alignment are essential to measure masses and lifetimes accurately. Some detectors measure neutral particles and invisible particles indirectly. Photons are neutral and leave no track in the inner detectors. They deposit energy in the electromagnetic calorimeter. Neutrons and neutral hadrons deposit energy mostly in the hadronic calorimeter. Neutrinos pass through the detector without interacting in most cases. Their presence can be inferred by missing energy. If the sum of the measured energies and momenta does not balance, a missing component may be present. That missing energy is a key signal for processes that produce neutrinos or other weakly interacting particles. Neutrino detection in specialized experiments uses very different techniques. Because neutrinos interact rarely, detectors need large volumes. A water Cherenkov detector uses a large tank of clear water surrounded by light sensors. When a neutrino interacts and produces a charged particle, that particle can travel faster than light moves in water. The charged particle produces a cone of light. Photomultiplier tubes record the light. The pattern and timing of the light allow reconstruction of the interaction. Liquid scintillator detectors use materials that produce light when charged particles pass. The light is collected and used to reconstruct energy and position. Liquid argon time projection chambers use a large volume of liquid argon. Ionization electrons drift under an electric field to wire planes. The drift time and the wire signals give a detailed three-dimensional picture of the event. Detectors for rare events, such as dark matter searches, use ultra-low background techniques. They are placed deep underground to reduce signals from cosmic rays. The materials used are chosen for low radioactivity. Shielding and active veto systems reduce remaining backgrounds. These experiments often measure tiny energy deposits and need careful control of noise and of environmental factors. Historical detectors gave the first views of particle tracks. Cloud chambers make tracks visible as a trail of condensed vapor along the path of a charged particle. Bubble chambers make tracks of bubbles in a superheated liquid. These visual detectors recorded images on film. Later detectors used electronic readouts that gave faster and more detailed data. Photographic plates and early counters played a role in many discoveries. Over time, the instruments became more precise and more automated. Detectors also use light sensors and electronics. Scintillators make light when a particle passes. That light is sent to photomultiplier tubes or to semiconductor light sensors. The sensors convert light into electrical signals. Electronics shape and amplify the signals. They digitize the signals and send them to the data acquisition system. Timing circuits measure when each signal arrives. Precise timing helps to associate signals from different parts of the detector to the same event. Simulation is a central tool in detector design and data analysis. Scientists build a computer model of the detector and of the particle interactions. The simulation produces virtual events that pass through a virtual detector. The simulated signals are processed in the same way as real data. By comparing simulation and data, scientists check calibration, acceptance, and backgrounds. Simulation helps to design detectors to reach the required sensitivity for a planned measurement. Detector design balances many factors. The cost, the required precision, the expected event rates, and the radiation environment all enter the choices. High radiation areas need components that resist damage or can be replaced. The innermost trackers see intense particle flux and must be built with robust technology. Calorimeters must withstand deposited energy and provide stable signals over time. Engineers and scientists work together to design systems that can operate reliably for many years. Large accelerator facilities need substantial infrastructure. They require power, water cooling, ventilation, and radiation shielding. Superconducting magnets need cryogenic systems to stay cold. Cryogenic cooling uses liquid helium to keep the magnets at very low temperatures. The control systems monitor beam position and machine parameters. Safety systems prevent accidental release of radiation or beam energy. Teams of experts operate the machine and the experiments around the clock while data-taking runs are active. Smaller accelerators and detectors serve many uses outside fundamental research. Tabletop accelerators provide beams for material study, for medical isotope production, and for testing detectors. Cyclotrons and linear accelerators are used in hospitals for cancer treatment. Industrial accelerators process materials and sterilize products. These applications use the same basic principles as large research machines, but in a form suited to the task. Finding a new particle often requires looking for a specific pattern in the detector data. Scientists reconstruct the four momenta and energies of detected particles. They form combinations of these measurements and calculate quantities that reveal the mass and decay properties of a parent particle. If a peak appears at a given mass value in many events, it can indicate a new particle. Careful checks of backgrounds and systematic effects are required before a claim of discovery can be made. Data from detectors grows quickly. Experiments must manage large volumes of information. They use computer farms and networks to store and process data. Analysis software reconstructs events, selects interesting cases, and computes final results. Teams of physicists examine the data and test hypotheses. They use statistical tools to measure how likely it is that an observed effect is genuine and not a fluctuation of the background. The combined work of accelerators and detectors has produced many important results. Experiments have measured the properties of known particles with high precision. They have found new particles and new processes. The instruments continue to improve. New detector technologies increase precision, speed, and radiation tolerance. New accelerator concepts aim for higher energy, higher intensity, or more compact designs. The physics goals drive the choice of machine and detector. To study rare processes, a high collision rate and large data sets are needed. To study heavy particles, high collision energy is necessary. To measure small effects, precise detectors and stable conditions are required. These choices shape the technical details of each project and the way the whole system is built and run. The knowledge and techniques developed for accelerators and detectors reach beyond particle physics. They influence medical imaging and treatment. They support materials science, and they drive innovations in sensors and electronics. The work needed to design, build, and operate these tools also trains engineers and scientists. The long-term effort to push the limits of observation and to record what particles do leads to new methods and new applications. Accelerators and detectors form the core of experimental particle science. They turn theoretical ideas into tests that can be measured. They create conditions where particles appear and then record what those particles do. The combination of careful machine design, precise detectors, and thorough data analysis makes it possible to explore the smallest parts of matter. The progress in these tools continues to open new possibilities and to provide the data that shapes our understanding of the particle world. The machines and detectors that let scientists study particles also gave us many tools that help people in daily life. The same ideas that let us find new particles help engineers build devices for medicine, for communication, and for industry. The work to design those machines created new materials, new sensors, and new methods to handle data. Those results moved from the laboratory into factories, hospitals, and research centers. One of the most widespread technologies comes from the control of electrons in materials. Semiconductors are materials that can guide electron flow in useful ways. Scientists learned how electrons behave in solids by studying atoms and particles. That knowledge led to the invention of the transistor. A transistor can act as a switch or an amplifier for electric signals. Many transistors made small devices possible. When engineers put many transistors together in a small area, they created integrated circuits. Integrated circuits are the building blocks of computers and phones. A key idea in semiconductors is to change how many electrons are free to move. This is done by adding small amounts of other elements to the material. The process is called doping. Doping sets regions with extra electrons or regions with missing electrons. At the boundary between those regions, a junction forms. That junction can control the flow of current. When a voltage is applied in a certain way, the junction lets current flow. When the voltage changes, current may stop. Engineers use these properties to make diodes and transistors. Manufacturing semiconductors requires precise control of tiny features. Engineers use methods to place patterns at scales of millionths of a meter. They use clean rooms and special machines to build layers of material and to etch patterns. Ion implantation, a technique that uses beams of charged atoms, places dopants into the material. This use of beams comes from particle accelerator technology. The methods that started in particle research now make modern chips that power many devices. Light is another area where particle science made a big impact. Understanding how electrons in atoms emit light gave engineers the knowledge needed to make lasers and light-emitting diodes. A laser produces a beam of light that is narrow in color and direction. Lasers work by causing many atoms or molecules to emit light in a coordinated way. The light is strong and well controlled. Engineers use lasers in surgery, in cutting and welding, and to send information through fibers for communication. Light-emitting diodes, or LEDs, are small light sources made from semiconductors. When current passes through an LED, electrons and holes recombine and emit light. LEDs are very efficient at producing light for many colors. They are used in lighting, in displays, and in signals. The development of LEDs used the same understanding of electrons and energy levels that particle science provided. Photon detectors and sensors also come from particle research. Photomultiplier tubes and semiconductor light sensors measure single particles of light in some cases. These devices are used in cameras, in medical imaging, and in scientific instruments. Advances in light sensors have improved digital cameras and instruments that measure faint light from distant sources or from small samples. Medical technologies benefited strongly from particle and quantum science. Magnetic resonance imaging, called MRI, uses the magnetic properties of atomic nuclei. The nuclei of some atoms act like tiny magnets. In an MRI machine, a strong magnetic field lines up those tiny magnets. Then radio waves are used to disturb the alignment. When the nuclei return to their original state, they emit signals. Those signals give information about the chemical environment and the structure of tissues. MRI produces detailed images of soft tissue in the body. It helps doctors diagnose many conditions. Positron emission tomography, called PET, uses particles that come from unstable atoms. A small amount of a radioactive tracer is put into the body. The tracer emits positrons, which are the antiparticles of electrons. When a positron meets an electron, they destroy each other and release photons. Detectors around the body record those photons and determine where the tracer is. PET gives images of metabolic activity. It helps doctors find tumors and to see how organs work. Accelerators make many of the radioisotopes used in medicine. Small accelerators, called cyclotrons, produce isotopes that decay and give signals useful in imaging. Hospitals and producers of medical isotopes use this technology to supply tracers for PT scans and for other imaging methods. Particle beams are also used in radiation therapy. High-energy beams of electrons or protons can target tumors. Proton therapy uses beams that deposit a large fraction of their energy in a narrow region. This allows doctors to deliver a dose that harms the tumor while sparing surrounding tissue. X-rays and computed tomography use high-energy photons to image the inside of the body. X-ray sources and detectors improved from research into radiation and particle detection. CT scanners take many X-ray images from different angles and combine them to form a three-dimensional view. These tools aid diagnosis and treatment planning. Imaging at small scales uses tools that rely on particle behavior. The electron microscope sends a focused beam of electrons onto a sample. Because electrons have a much shorter wavelength than visible light in these instruments, they can resolve much smaller details. Transmission electron microscopes let electrons pass through thin samples. The electrons that emerge form an image on a detector. Scanning electron microscopes send a beam across the surface. Secondary electrons emitted from the surface give information about the structure. These microscopes reveal details at scales far smaller than what light microscopes can show. The scanning tunneling microscope is a device that uses quantum tunneling. A sharp metal tip is placed very close to a surface. When a small voltage is applied, electrons can tunnel between the tip and the surface. The tunneling current depends on the distance to the surface and on the local electronic structure. By moving the tip and recording the current, the instrument builds an image of the surface at the atomic level. Scanning tunneling microscopes helped scientists to study atoms on surfaces and to manipulate atoms in controlled ways. Tools that use beams and detectors also support materials science. Synchrotron light sources are a kind of accelerator that produces intense beams of X-rays and ultraviolet light. Scientists use those beams to study the arrangement of atoms in materials and to probe electronic structures. The methods let researchers find the positions of atoms in crystals, study proteins, and measure how materials change under stress. Synchrotron facilities are used by many fields beyond particle physics. Precise timekeeping came from studies of atomic transitions. Atomic clocks use the frequency of radiation that atoms emit or absorb when electrons change energies. Cesium atomic clocks use a transition that gives a stable frequency standard. Modern atomic clocks measure time with extraordinary precision. Such precision is crucial for navigation systems. The global navigation systems used in phones and transport rely on accurate timing to locate positions. Precise time also helps communication networks and finance systems to coordinate events by shared time references. The need to handle large amounts of data in particle experiments changed computing and data management. Early particle laboratories developed networks to share data and documents. One of those projects grew into tools that are now used widely across the world. The need to store, move, and analyze very large data sets pushed advances in distributed computing. Grid computing and cloud computing methods grew from the need to run complex analyses on many computers at once. Software for event reconstruction and pattern recognition came from detector analysis. These programs find tracks and clusters in noisy data. The same methods help in medical image analysis and in industrial inspection. Machine learning techniques that are now common in many fields had early uses in particle data classification. The collaboration between physicists and computer scientists created tools and best practices that spread to other areas. Sensors and electronics developed for detectors found uses in many industries. Fast electronics, low-noise amplifiers, and precise timing circuits came from the need to record signals from detectors. These circuits are now part of radar systems, of medical instruments, and of communication equipment. Cryogenic technology developed for superconducting magnets and for detectors supports systems in quantum computing and in sensitive measurement devices. Accelerators are not only research tools. They have many industrial and medical uses. Electron beam accelerators sterilize medical equipment and food. They do this by exposing items to a controlled dose of radiation. Material processing uses accelerators to change surface properties. Ion implantation machines place dopants into semiconductor wafers to make microchips. These industrial processes come from the same physics and engineering that built research accelerators. Security and inspection systems use particle detectors. X-ray scanners at ports and airports use detectors to record transmitted or scattered radiation. Systems that check cargo for hidden materials use neutron or gamma sources and detectors to reveal composition. Radiation safety and monitoring systems use detectors developed from particle physics methods. The work on small-scale quantum effects also led to new technologies that use superposition and entanglement. Quantum computing aims to build machines that process information using qubits. A qubit can be in a superposition of the states 0 and 1. When many qubits are controlled and linked, the system can perform some calculations that are very hard for ordinary computers. Engineers try to build qubits with long coherence, meaning the qubit keeps its quantum state long enough to perform operations. The challenges include errors and interaction with the environment. Scientists develop error correction methods and materials that reduce noise. Quantum communication uses entanglement and quantum states to share keys for secure communication. In quantum key distribution, a sender and a receiver use quantum states to generate a secret key. Any attempt by an eavesdropper to measure the states changes them and can be detected. This method gives a level of security that depends on physics rather than on mathematical assumptions. Practical systems are under development and are already in limited use for high-security links. Quantum sensors use quantum states to measure small fields, small displacements, or small time changes. These sensors can be more sensitive than classical instruments for certain tasks. They use atoms, superconducting circuits, or other quantum systems to detect tiny signals. Applications include gravity measurement, magnetic field sensing, and precise time transfer. Building new quantum devices requires advances in materials, in control electronics, and in cooling. Many quantum devices operate at very low temperatures with superconducting circuits. Cryogenic techniques and low-noise electronics that developed in particle and low-temperature physics help build these devices. Training and skills come from long-term research programs. Building accelerators and detectors trains engineers, technicians, and scientists. Those people move into industry and into medical work. The knowledge they develop spreads to companies and to universities. The process helps create new companies and new jobs that use advanced sensors, electronics, and software. Research often takes many years before it becomes a product. A new idea may need long development, testing, and engineering. Safety and regulation matter, especially in medical and industrial uses. Devices that affect health must pass tests and approvals. The transition from laboratory result to product requires design for reliability, cost control, and manufacturing methods. The benefits of particle science appear in many parts of society. Medical tools save lives and improve diagnosis. Communication systems connect people across the world. Industrial processes become faster and more precise. Scientific instruments let researchers discover new materials and new drugs. The steady investment in basic research leads to new capabilities over time. The tools and methods developed for particle studies also prepare us for new challenges. As detectors become more precise, they support better imaging and more sensitive measurements. As accelerators become more compact and efficient, they can serve hospitals and industry more widely. As quantum devices improve, they may bring new ways to compute and to secure communication. The flow from a basic idea to a working technology involves many steps. It often needs collaboration across fields. Physicists, engineers, chemists, and computer scientists work together. The work includes design, prototyping, testing, and scaling to production. Each step requires careful measurement and verification. This process ensures that the device meets the needed performance and safety standards. The long view shows that knowledge about the smallest parts of matter builds tools that matter at larger scales. New detectors lead to better medical images. New accelerator techniques lead to cleaner industrial processes. New quantum methods lead to sensors and to new computing ideas. The exchange between basic research and practical use continues in many laboratories and in many companies. The technologies from particle science have practical value today. They also open paths to new devices and new measurements. Engineers and scientists continue to refine the methods, to reduce costs, and to increase the performance of the tools. The work that started in the search for fundamental particles now touches many parts of daily life and of modern industry. The same curiosity that drove the study of particles continues to drive the development of technologies that help people and advance knowledge. That work leads scientists to new questions about the smallest parts of matter and about the universe as a whole. Some of these questions are about how the known rules fit together. Some are about what we still cannot see. Scientists use experiments, observations, and careful thinking to try to answer these open questions. The work takes many kinds of tools and many people working together. One deep question is how the rules of quantum mechanics join with the rule of gravity. Quantum mechanics describes particles and forces at very small scales. Gravity is the rule that shapes the motion of large masses and the shape of space and time. The two sets of rules work very well in their own ranges. but they do not fit together in a single simple description. The search for a theory that unites them is a major goal. Gravity behaves in a way that depends on space and time. Quantum mechanics uses probabilities and wave descriptions for particles. When scientists try to apply the quantum rules to gravity, difficulties appear in the calculations. The problems become large at very small distances and very high energies. These scales are far beyond what current machines can reach. Still, physicists use mathematical ideas to try to build a consistent theory. Several approaches exist. Each approach has its own methods and its own challenges. One approach looks for a description in which the basic constituents are not only particles but also other objects that give rise to forces and space. Another approach tries to quantize the geometry of space itself. There are other proposals that change assumptions about how space and time behave at the smallest scale. All these ideas must match the many successful results of quantum mechanics and of gravity in the ranges where each one works. Designing tests that can show which idea is correct is hard. Some tests come from high-energy experiments, but many come from precise measurements and from astronomical observations. Black holes present a strong test for ideas that join quantum mechanics and gravity. Inside a black hole, gravity is extreme. The mathematical description of black holes leads to questions about what happens to information and to the nature of space near the center. The study of black holes and of the radiation they emit connects gravity, quantum mechanics, and thermodynamics. Observations of black hole mergers and of gravitational waves give new data to test ideas. Precise astronomical measurements of black holes and of the early universe also give clues. Another big question is the identity of dark matter. Many observations show that the visible matter in the universe is only a part of the total. Galaxies rotate in a way that needs more mass than the stars and gas provide. Galaxies in clusters move with speeds that need more mass to hold them together. Light from distant objects bends around unseen mass. The pattern of the faint glow left from the early universe contains details that point to extra matter not seen directly. This extra matter is called dark matter. Dark matter does not give off light. It does not absorb light in a way that we detect easily. Finding what dark matter is made of is a major challenge. Scientists have proposed many candidates for dark matter. Some candidates are heavy particles that hardly interact with ordinary matter. Other candidates are much lighter particles that interact very weakly. Some ideas propose a new type of particle that was created in the early universe. Each candidate suggests different kinds of experiments to find it. Some experiments sit deep underground to shield out ordinary radiation and look for tiny signals from rare collisions between dark matter and atomic nuclei. These are called direct detection experiments. Other tests look for signals from dark matter that collide or annihilate and produce light or other particles. Such searches use telescopes that collect light, X-rays, or gamma rays. They also use detectors that record high-energy particles arriving from space. A third route is to try to make dark matter particles in accelerators. In that case, the particle would appear as missing energy in a collision together with known particles. Each route has its own technical challenges and background signals to control. Another mystery is dark energy. Observations show that the expansion of the universe is speeding up. The cause of this acceleration is not known. One simple possibility is that space itself has an energy that acts like a repulsive pressure. This idea fits the data in a simple way. Other ideas propose a new field that changes with time. Some proposals change the rule of gravity on very large scales. To decide among these ideas, scientists measure the expansion history of the universe and the growth of structure in many ways. They measure the brightness of distant exploding stars and the pattern of galaxies across great volumes. They measure how light is bent by mass. The data sets grow with new surveys and new telescopes. Neutrinos raise more questions. Neutrinos are very light particles that pass through matter easily. Experiments have shown that neutrinos change type as they travel. This change means neutrinos have mass. The exact size of their masses is still unknown. Another question is whether a neutrino is its own antiparticle. If neutrinos are their own antiparticles, certain rare decays could occur that would show a net change in the number of electrons emitted. Scientists build experiments to look for such processes. Finding a positive result would change the way we think about particle identities and about how the imbalance between matter and antimatter in the universe was created. The observed dominance of matter over antimatter in the universe is a deep puzzle. The laws of physics seen in many experiments are almost symmetric between particles and antiparticles. Yet the universe today has far more matter than antimatter. Some processes in the early universe can produce an imbalance if certain conditions are met. These conditions involve differences in how matter and antimatter behave and processes that occur out of thermal equilibrium. Finding the mechanisms that produce the imbalance requires studying rare particle processes, measuring small differences in behavior, and understanding the early history of the universe through cosmology. The Higgs particle raises further questions. The Higgs gives mass to some particles through its interaction with them. But the value of the Higgs mass seems small in a mathematical sense compared with very large energy scales. Explaining why the Higgs mass has the size it does is a focus of theoretical and experimental work. Some ideas introduce new particles or new symmetries that keep the Higgs mass stable. Other ideas change the way the Higgs arises. Experiments at high-energy colliders test whether new particles exist that support these ideas. Precision measurements of the Higgs properties can reveal small differences from the simplest expectations. Searching for new particles and new forces continues. Particle colliders, cosmic ray detectors, neutrino experiments, and precision atomic measurements all play a role. Each experiment tests parts of the theory. Some tests look for rare decays. Some tests look for tiny shifts in energy levels. Some tests look for unusual signals in cosmic rays. The combined program builds a network of constraints on possible new physics. Practical challenges appear in building the instruments needed for progress. A larger collider needs long tunnels, strong magnets, and stable beams. A more sensitive dark matter detector needs ultra-clean materials and deep underground sites. A precise neutrino experiment needs enormous detectors placed at long distances. These projects require large teams, careful planning, and long time scales. They also require funding and international cooperation. The scale of the effort prompts discussions about priorities and about how to balance different approaches. New types of experiments are also rising. Precision measurements with atoms and ions can test subtle effects of new physics. Atomic clocks and atom interferometers measure time and motion with extreme accuracy. These methods can probe tiny forces and tiny changes in fundamental constants. Tabletop experiments can test gravity at very short distances. Laser interferometers and space-based detectors can watch for waves in space-time from distant events. Combining many different types of tests increases the chance to find new effects. Quantum computing and quantum communication are both scientific goals and practical technologies with open challenges. Quantum computers use quantum states to process information in ways that are not available to ordinary machines. Building a useful quantum computer requires many qubits that keep their quantum states long enough to perform operations. The main obstacles are noise and loss of coherence. When a qubit interacts with its environment, the quantum relation between its parts can be lost. Scientists design materials and control systems to reduce noise. They also build error correction methods that can protect quantum information. Error correction needs extra qubits and careful design. Scaling up to many qubits while keeping errors low is a major engineering task. Quantum communication uses quantum states to share information with security guaranteed by the laws of physics. The technology is already in limited use for secure links. Wider use needs robust hardware and networks. Quantum sensors promise higher sensitivity. They use quantum states to measure fields and distances with extreme precision. These devices need stable conditions and careful control of noise. The foundations of quantum mechanics remain an area of active thought. The formal rules give precise predictions, and experiments confirm those predictions again and again. But some questions about how definite outcomes appear from quantum possibilities still attract discussion. Some approaches focus on the role of the measurement device and on the process called decoherence. Others pursue different conceptual frameworks. For practical work, scientists use the rules to design experiments and devices. For deeper understanding, philosophers and physicists explore the conceptual questions. The dialogue between ideas and experiments continues. Data and analysis raise their own open questions. Modern experiments produce large amounts of data. The tools to store and analyze data must be reliable and accessible. Machine learning methods help to find patterns in data, but their use requires care to avoid bias. Reproducibility and openness in data and in analysis tools support trust in results. The training of new scientists in data methods is a continuing task. Ethics and responsibility enter large projects. Experiments need to meet safety standards. The environmental impact of big facilities must be considered. The benefits of research need to be explained to society. International cooperation, transparent planning, and public dialogue help to secure long-term support. The training and education that come from large projects also provide broad social benefits. Many open questions call for teamwork across fields. Particle physicists, astronomers, nuclear physicists, condensed matter scientists, and engineers often work together. Each field brings its tools and its questions. The combination of different perspectives can open new paths. For example, techniques from condensed matter physics help build quantum devices. Methods from particle physics data analysis help in astronomy. The crosstalk between fields accelerates progress. Funding and long time scales require effective planning. Building a major facility can take many years of design and construction. The work needs stable support and careful review. Smaller projects and tabletop experiments also provide valuable results. Balancing large-scale and small-scale work is part of an overall strategy to advance knowledge. Training new scientists and engineers is central. Large projects educate students and early career researchers in design, construction, and analysis. The skills they learn are useful beyond academia. The training supports industry and medical applications. Long-term investment in education strengthens the community and increases the capacity to tackle future challenges. Open questions have practical as well as conceptual importance. Finding dark matter would explain how structure in the universe formed and how galaxies behave. Understanding dark energy would change the picture of cosmic evolution and might affect our view of the long-term fate of the universe. A quantum theory of gravity would unify two great pillars of physics and might reveal new phenomena at the smallest scales. Progress in quantum technologies could change computing, communication, and sensing. The path forward combines new instruments, careful experiments, and strong theory. Building better detectors and better telescopes expands what can be seen. Designing precise laboratory tests can probe subtle effects. Developing new theory can suggest specific signals to look for. The close loop between theory and experiment is how many discoveries have happened in the past. Many questions remain. The effort to answer them is ongoing. Scientists design experiments, build instruments, collect data, and analyze results. They share methods and results with others. The work is slow at times and fast at other times. It depends on careful measurement, honest reporting, and continual testing. The combination of steady work and open curiosity drives the search for answers about particles, forces, and the universe.